Yes, hello. Thank you for listening to another episode here at the Quetzal Talk. Now, today, we're going to be talking about the Z machine. It's this machine that's being created around in our region or in the Sandia labs around, I think, Albuquerque. And it's this incredible machine that they're going to use for some type of astronomy. I don't know. We have Chris here on the line. Hello, Chris.
Hi, nice to be here. Thank you for inviting me.
Hell yeah. Well, thanks for chatting with us a little bit about this machine, man. And can you go ahead and let us know a little bit about you, your name, and what you do and stuff?
Sure. So my name is Chris Seagle. I'm a research and development manager at Sandia National Laboratories. And my team, I lead a team of people who do experiments on the Z machine. Mostly material physics experiments. So we study properties of materials that are subject to extreme environments that's generated by the Z machine. So the Z machine is a really unique facility. It's actually the largest pulse power facility in the world. Mm-hmm. And what pulse power is, it generates very high electrical currents in very short time periods.
Right.
So, you might be using a hairdryer that pulls like a couple amps out of the wall. The Z machine can deliver millions of amps to an experiment or a target that we're interested in. And when you deliver that much current to a target, basically it heats up, it vaporizes, ultimately it explodes. Mm-hmm. And so we look at how that material explodes and use that to learn about how that material behaves in, very high temperature environments or very high pressure environments. Mm-hmm. Pressures and temperatures that simulate the inside of the sun.
Hmm. And so all this energy, how is it created? Is it created using the regular electrical grid system that we have, or do you guys use something else to create this energy?
That's actually correct. We pull the energy right off the electrical grid here in Albuquerque. And, basically how it works is we have, big capacitor banks, and capacitors are just basically metal plates that can store energy. We pull energy off of the grid and store it in these capacitors. Mm-hmm. And we just build up a lot of energy storage, and then we release it all at one time so that, basically it amplifies the current by millions of times compared to what you could normally pull off the electrical grid.
Right. Wow, man. And since you guys use all these amps of energy, is it dangerous to the world? I mean, can you guys accidentally explode the world or something?
No, we're not going to accidentally explode the world. I mean, it's a lot of energy, but it's released very fast. So the total amount of energy that is being released is 20 or so megajoules. So to give you a reference for that, it's a couple sticks of dynamite. Right. So we're not going to blow up the world, but right. we do blow up a lot of metal.
Oh, nice. And can you break it down on how do you guys use this machine for astronomy purposes? Right, I hear that you guys are using it now for to try to look up other super planets or some super Earths. That's what I was.
Yeah, that's right. So. So we look at what the Earth is made of, and we know what kind of rocks are on the Earth, and out in the universe, there's all kinds of exoplanets.
Right.
And we want to learn, what are those exoplanets made of? Would they be able to support life? And one way of making some of those inferences is to learn about or try to infer what those planets are made of, and what are the temperatures of those planets. Might they have an atmosphere? So one way we go about doing that is looking at the properties of minerals that those planets are likely made of at conditions, pressure and temperature conditions that are thought to be present, in those planets.
Mm-hmm.
So one thing we did in particular is look at a mineral that's called Bridgemanite. Bridgemanite is basically a magnesium silicate mineral. It's basically the most common mineral that you'd find in the interior of the Earth.
Mm-hmm.
It's so it's a very common mineral on Earth, and we wanted to learn, well, what temperature does this material melt at?
Mm-hmm.
Especially at very high pressures. So what we did is we took pieces of this mineral, and we used the Z machine to accelerate a piece of metal, which we call a flyer plate,
Mm-hmm.
and smack it into that mineral. Which basically launches a shock wave into that material and compresses it to really high pressures and temperatures.
Mm-hmm.
And then we look at, how does it melt? And we use that information to try to learn about the interiors of exoplanets. The way that it works is when you run these like millions of amps of currents along a metal plate, it generates basically a magnetic force and an ablative force. So you run all that current on a plate, and the plate starts to melt and vaporize, and a magnetic field basically pushes that plate forward. And so you can accelerate these metal plates up to, tens of kilometers per second. So it's, basically like meteorite impact speed.
Right. Okay. So you guys determine how this material melts or whatnot, and then how do you guys use the Z machine to figure out what materials are in these super Earths or whatnot?
Yeah. So basically, the connection between the material properties that we infer from these experiments on the Z machine and what's actually out there in the exoplanets is through essentially modeling and observations.
Mm-hmm.
So astronomers will go and observe these exoplanets, and they're very, very far away. So it's hard to measure a lot of properties of these planets, but what they can tell us is the mass and the radius of these planets.
Mm-hmm.
And basically with the mass and the radius, you can get density. So, the density of the Earth is something like 3 grams per centimeter cubed.
Mm-hmm.
So if we find an exoplanet that is, roughly 3 grams per centimeter cubed, there's a pretty high likelihood that that planet is made of stuff that's similar to the Earth.
Right.
Right. So we can take the information we learn from the Z machine to then try to model the properties of these exoplanets, many of which are, called super Earths because they tend to be much larger than the Earth. So, 10, 15 times bigger than the Earth. And because of their bigger mass, they have, of course, much higher pressures on the inside. So the way that the materials behave inside of those exoplanets compared to the Earth is a little bit different because there's a lot more stuff, basically piled on top of the planets.
Right.
So we need to know the properties of the minerals and the material that's making up those exoplanets at very high pressures higher than, that are experienced in the center of the Earth.
Wow, man. And I was also wondering how did this machine, do you guys send a laser to the planet, or how does this machine bring back that information?
Yeah, so we use lasers as basically a tool to measure how fast things explode, and it's based on the Doppler effect. So if you're not familiar with the Doppler effect, basically when you hear, if you're standing on the side of a train track and you hear a train go by, the pitch of the train whistle, basically changes tune as it's going by.
Kind of like
right?
wave
And
elasticity.
so, yeah, so the same thing happens to light. When light bounces off of something that's moving, its wavelength changes just a little bit. So, it might go from red towards blue. And so we use these lasers to basically measure that Doppler shift, and that using that we can see, well, how fast is the material moving, how fast is the shock wave going, how fast does it explode, and people have come up with really clever ways of taking that information and inferring all kinds of physical properties of the materials, like their density, the pressure, whether or not it's been liquid, melted, or vaporized.
Right. And I was also wondering, I mean, we're trying to figure out about these super Earths, right? But what's the end goal? Because obviously we have no space travel machines, we can't travel that fast to get to these places. So what is the end goal on trying to figure out what's on these super Earths? Is it just for knowledge?
Yeah. So it's of course expanding knowledge. I mean, it's one of the greatest questions I think of our time is there life somewhere else in the universe?
Right.
And so one of the contributions of the Z machine towards that is trying to narrow down the zoo of exoplanets. Where might life be most likely to exist? Right, because astronomers have now discovered thousands of exoplanets,
right,
and probably only some very small fraction of those might actually be able to support life.
Right.
Now, that doesn't mean that there's life on any of those planets, but if we can help focus, the most likely candidates, then we can apply basically our resources to, the most exciting or likely candidates to try to figure out if there could be life there, and of course the ultimate question is there life out there.
Right. Yeah. That would be crazy, huh? If there was some type of especially if it was intelligent life, that would be some type of. But
yeah. So I mean, most of these interesting exoplanets are awfully far away. Many light years away. So that's far enough that you and I are never going to travel there.
Right.
But it doesn't make communication impossible, actually. So, an exoplanet, if it had life that was, say, 10 light years away, if those aliens or beings that were there had a strong enough radio receiver, they could be sitting around watching,
right.
late 90s television right now.
Right. Do you ever think we'll figure out a way to speed up information faster than the speed of light, or do you think that's just a cap?
Yeah, I think the speed of light is a cap. It seems to be like a hard cap on communication and certainly on travel. There's just no way to go faster than the speed of light.
Yeah, man. And also, what can you let us know why initially or how do you think of building a machine like this? Do you know like who got the idea and what was the initial purpose of it, or how did people think of starting this project?
Yeah. So the Z machine has been around for quite a while at Sandia. So 20 years or so, and even before that, there were predecessor machines that would basically designed to generate these really high currents.
Right.
The original motivating factor to build these machines is to simulate the effects of nuclear weapons.
Okay.
So they generate, as I mentioned, really high pressures and temperatures. And one of the core missions of Sandia is to maintain the security and reliability of nuclear weapons.
Right.
So we do a lot of experimental testing on the Z machine to try to basically ensure that our nuclear deterrence is strong.
Oh, wow. That's crazy. So after this energy, right? This whatever amperage you guys use, I forgot, but what do you guys do with that energy afterwards? I mean, yeah, you guys send the laser and that's where all the energy goes, or do you guys?
So most of the energy that is delivered to these targets is basically just dissipated in the end. So the experiment basically explodes and turns into vapor, and then just gets deposited as dust around the machine.
Right.
So we need to go in there and basically sweep up the dust after the experiment.
Okay. So you guys also have a lot of astronomers and astrophysicists working with you on this project, or?
Yeah. So we have a team of people that some of them are experimental physicists, and others are astronomers, and others are experts at computer models, building computer models of planets.
Right. That's crazy, man. And also, I was hearing, man, I don't know if you know anything about this, but China's trying to build one of these, right? I don't know if you guys know anything about that. Is that something, a competition that could be dangerous, or is it just, let them do it, whatever?
Yeah, I don't know if it would be, if I would call it dangerous, but yeah, so pulse power is of interest to lots of other countries around the world, including China. And, I think that's because these pulse power machines, like the Z machine, have so many applications and, very cool science that comes out of it. So, I think it's a healthy competition to have some competition at the international level.
Right. Yeah, man. And is there anything else that you can let us know about this that we don't know, or? I mean, because I'm asking the questions that just come up to me, but I mean, I don't know if you have any other information that would be, pretty interesting about this machine.
Yeah, sure. So I can talk a little bit about, other types of experiments that the machine does. So we kind of focused on, material physics experiments, but that machine is actually pretty versatile to do other kinds of experiments too. So one of those is fusion. So you've probably heard about fusion before. That's basically how the sun creates energy by taking, different types of atoms, pushing them together, and then releasing a bunch of energy.
Right.
So we do fusion experiments on the Z machine too, and those experiments are actually pretty cool because instead of accelerating flyer plates to smack them into samples of interest.
Right.
They basically take deuterium, which is a type of hydrogen, fuel, and implode it. So it's like an explosion that goes in on itself.
Oh.
And then try to get that fuel to fuse and then release a whole ton of energy in the process. So it's like an implosion followed by an explosion.
Damn. And what does it fuse with, or how do you guys just?
Yeah, so the deuterium is again a type of hydrogen.
Right.
Basically, if you can squeeze two hydrogens close enough together, they will fuse and create helium.
Oh, wow! Isn't that what the sun has?
Yeah, so you can turn one element into a different element, and in that process, it releases a whole bunch of energy. So that's kind of a really exciting prospect for, the future of energy security in this country. If we could harness fusion to, power our grid, that would be a huge, benefit in energy security for our country.
How so? How so? Can you let us know a little bit more about that?
I'm sorry, what was that?
Yeah, how would it be better for us if we could do that?
Oh yeah, so if we could do that, then then we could use basically we would have almost unlimited energy. So right now, we're basically using fossil fuels,
right?
Which is supplemented by some degree to renewable energies like wind and solar, but we're still burning an awful lot of oil and coal.
Right.
If we could use fusion energy, the source of that energy we could get from seawater. So you can pull hydrogen out of seawater, and if you can then use fusion to turn that hydrogen into helium and energy, it's almost an unlimited energy source. So it would reduce our reliance on fossil fuels. It would be better for the environment.
Right.
All kinds of benefits.
And you won't take the water out the ocean? Like, would there be less water in the ocean within time?
Yeah, well, that's true, but the amount of water that you'd be taking out of the ocean for a given amount of energy, it would be really, really small. So, even if our whole country was powered by fusion that was generated from seawater, I don't think it would make a dent on the level of the oceans. And if anything, it's because of climate change, we're seeing sea level rises.
Right.
Sea level rising, which itself is not such a good thing. So, pulling water out of the ocean may not be such a bad thing.
Right. Okay. Well, thanks, man. Sounds like this steam machine can be used for a lot of good things for our country, man. And it's really good that you guys are working on that, and that we have this type of projects happening for our country to, make it better and to try to find better things for the future of humanity, right?
Yeah, no, we do a lot of really cool science and engineering here at Sandia, and a lot of the work we do is cutting edge of science. We want to benefit the people of this country to protect and enhance everyone's lives. And in the details of what we're doing are pretty fun. So it's fun to come to work and use the Z machine and blow things up, and also feel the real impact that has on our lives here.
Right. Damn. Well, I bet you it is a real exciting job, man, and I hope that you guys continue and further the knowledge of this thing, and I wish y'all the best with all your endeavors, man. And I don't want to take up more of your time because I know y'all are busy people and y'all got stuff to work on. So we want to go ahead and thank you, Christopher Seagle, for talking to us here at Quetzal Talk, and also Mr. Neil for contacting us and providing us with your contact, man, so we could go ahead and learn about this machine. And it's very interesting, man. I really thank you for chatting with us, man.
Well, thank you. It's been a pleasure.
Cool. Well, we'll go ahead and let you guys go. Thank you so much. Thank you, Neil.
Okay, thank you.